Okay, everyone, in this video lecture, we're going to discuss the concept of chemical reactions. All right, so when a chemical reaction does occur, we're going to see the following three things happening during them. All right, first is we're going to get the formation of new bonds. All right, bonds that have never existed before. So if you think about it, if I give you a generalized equation, let's say A plus B produces C plus D. All right, we are going to have to modify the bonds in A and B in order to create new ones to get our products of C and D. So it's going to be some type of bond formation. But in order to get that, we're going to also have to break bonds. So the bonds holding together the atoms in molecules A and B will be broken and then reformed into C and D. And pretty much you're always going to get the formation of new substances, things that are different from what you started with. No matter what the reaction is, something as simple as burning firewood. You're going from wood to heat, flame, and ash. You're still changing something from one form to another. So you're going to see all three of those things happening during any type of even simple chemical reaction. Now, all chemical reactions in our body are making up the term what we refer to as metabolism. All right, so again, this is going to be all chemical reactions that occur within the body. And trying to tag into what we learned about originally this year of the concept of homeostasis, all chemical reactions happening in your body, building as well as breaking down. We call them, next unit, we'll call them dehydration, synthesis, and hydrolysis. You have to have these two types of reactions in check in order to maintain homeostasis within the body, within a cell, and then within an organ, within a tissue system, and within the whole entire body. Everything needs to remain in check. If you have one type of reaction that's happening much more than the other, something is going on in the body. Now, when we start to look at chemical equations, especially as we move into eventually photosynthesis and cell respiration, we're going to again look at these simplistic formulas. A plus B is going to give us C and D. We're going to have what we call, first off, reactants and products. Reactants are always on the left-hand side of a formula that you see up here. All right, so A and B, or whatever was over there, it could be 4, 5, 6 different things. Whatever you find on the left-hand side of the formula is or are the reactants, and that are going to be forced to change. Then on the right-hand side of the chemical reaction arrow, we're going to have the products. So again, products are going to be on the right-hand side of the arrow. That is whatever new items that you are forming as a result of this reaction. So reactants on the left of the arrow and products are always on the right. And then as we, instead of just looking at like A or B, let's start looking at some formulas here. When you start to see formulas in an equation, all right, we're already familiar with why it says C6H12O6. We know it's a combination of all of those elements combined together in some form, right? And this would be a polar covalent bond. All right, we're going to try to give some names now to the specific numbers. So the term subscript, and again, I draw your attention to that first part, sub. I think of a submarine, something low, underground, subterranean, all right, at that point. That's referring to the smaller indented numbers that you see after each element. And that means that in one glucose, so C6H12O6 is glucose, in just one little speck of sugar, you're going to have 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. And that's in just one grain or molecule of glucose, period. But you're never going to have just one of something those times. You're going to have numerous ones. So you're going to start to see them also written like this down below. All right, where you have the number 5 placed in front of the formula. That number is called the coefficient. All right, and that's the number you put before a chemical formula, and what it's referring to is how many of that specific chemical formula do you have. So in this instance, we have 1, 2, 3, 4, 5. All right. Oh, there you go, 5 molecules of glucose. So once you put the coefficient in front, I can start asking you several different questions. I can say, how many molecules of glucose are there? The answer will be 5. But then I could also ask, how about this? How many total atoms of carbon do you have in that formula? It's not 6 anymore. All right, what you got to do is you have 5 molecules of glucose, and in each molecule you have 6 carbons, so you got to multiply. 5 times 6 would be 30 carbons. And you do that for the rest. All right, so how many hydrogens? I'll give you a second to do that math. You're going to have 60 hydrogens. 5 times 12. And how many atoms of oxygen? We're going to have 30 also. So 30. Oh, so you just have to do multiplication. So pretty simplistic. Now, bringing our attention back to chemical equations, I'm going to throw something out there at you. One of the laws of thermodynamics I know you've heard before. Energy can neither be created nor destroyed. So what that means is you really can't destroy anything. All you're doing is converting something from one form to another. Even when you burn wood, let's say in a fire pit out in your backyard, right? What's happening is you're just turning the energy and all the chemical bonds in that wood into 3 other things. Light energy, heat energy, and ash, right? Believe it or not, even though it's gone after a while, that light and heat energy still does exist. It's just moved on to another area. So that heat has dissipated into the atmosphere, but it's still there. The light given off by the fire, just like as the light you see from stars, is given off and is traveling out there into the universe now at some point. It's kind of crazy to think about, but you really aren't destroying anything. You're just converting it. So whatever you see then on the left-hand side of a formula is also going to be on the right-hand side, just in some different fashion. So for example, on the left up here, I have between methane and 2 molecules of oxygen, I have 1 carbon atom right here. Since there's no subscript, you just think of it as 1. On the right-hand side, there still is only 1 carbon atom, but now it's in the form of carbon dioxide, CO2. See how it's still there? It's just in a different form. On the left-hand side, we have 4 hydrogens, which are right here, part of methane. But on the right-hand side, they're now part of water, and I have 2 molecules of water. Each water molecule has 2 atoms of hydrogen, so 2 times 2 is 4. So we can see we still have 4 hydrogens. And finally, for oxygen on the left-hand side of the formula, it is in the form of 2 breathable oxygen molecules. So 2 times 2 is 4. Now on the right-hand side, the oxygen is actually split between the 2 different products. So between the 1 CO2 molecule that we have, so again, there's 1 there because there's nothing written in front. All right, we have 2 atoms of oxygen. And then for the water, we have 2 times 1 per each water molecule is 2. So 2 plus 2 is 4. So you should always be able to count the same number of atoms of an element on the left-hand side as well as the right-hand side of a formula. They're just going to be part of different reactants versus products. All right, to finish out with some review here for just counting atoms, I have 3 compounds here listed. All right. We want to be able to say how many there are of that particular compound or molecule if it's held together by a covalent bond, all right, and then also how many total atoms. So if I start with the first one, 2H2SO4. So I have 2 molecules of what we call hydrogen sulfide, all right, at this point. Sulfur, it's really sulfuric acid is what it is. So I have 2 molecules of sulfuric acid. But then if I want to talk about how many atoms there are, for hydrogen, there are going to be a total of 4. Because I have 2 times 2 is 4. For sulfur, in this formula, I'm going to have 2 atoms. 2, nothing there, so that's a 1. 2 times 1 is 2. And then for oxygen atoms, we're going to have 2 times 4, and that's 8. So in this formula, I have 2 molecules of sulfuric acid, and then I have 4 atoms of hydrogen, 2 of sulfur, and 8 of oxygen. All right, let me throw some crazier ones at you now. The next formula, 2Al2, and SO4 in brackets, followed by a 3. So what that means in general is you're going to have 2 aluminums that have 3, in some fashion, SO4s connected to them. All right, that's what it ultimately means, but I don't really care about that right now. I just want to count atoms. So I have 2 of this Al2 SO4 3 formula. But then if I want to count total atoms, I'm going to have 2 times 2 aluminum, which is going to be 4. And now when you see brackets, all right, so right here, and if there's a number after it, what'll be easier for you to do is first multiply that. So I have 3 SO4s. So that means I'm going to have 3 sulfurs, and 4 times 3 is 12. So I'm going to have 12 oxygens. But now you need to, that's just in those brackets. Now you need to multiply those numbers by your coefficient out front. So I'm going to have 6 sulfurs. All right, and then what do we got? 12 oxygens times 2, and that's going to be 24 oxygens. All right, and in the last example, we have 2 Mg3s, PO4 2s. All right, overall of that formula, I have 2 units, molecules if you want to use that term, of this particular formula. But if we count our total atoms, coefficient times subscript, I'm going to have 6 magnesiums. Then I see brackets, so I'm going to do my multiplication first again. 2 times 1 is 2 phosphorus. 4 times 2 is 8 oxygens. But then we're going to multiply that by the coefficient. So I'm going to have 2 times 2, and that's going to be 4 phosphorus atoms. And then finally, 8 oxygens times 2, which is the coefficient, and I'm going to have 16 oxygen atoms. All right, so either on the left-hand side or right-hand side of the formula, you would still do this the exact same way to figure out how many atoms there are of any particular compound/molecule. Thank you very much.